right, so this is the second video for part 1 of Taylor and Maclaurin series in BC Calculus. And so we have previously introduced ourselves to the concept of what Taylor series are used for, and then we have also learned some of the special Maclaurin series that are good to memorize. So in these examples, we're just going to be working some problems that have to do with Taylor series. So the first one says to find the fourth order Taylor polynomial that approximates y equals cosine of 2x near x equals 0. All right, so I'm actually going to work this problem in two ways so that you'll be able to see both approaches to them. So the first way that I'm going to do it is the way that we originally came up with the concept of a Taylor series, which is we know that our function, if they say fourth order, then we're going to go all the way to x minus a to the fourth, to that term. Now, since we're centered at 0, that means we're going to go all the way to our c sub 4 times x to the fourth term. Or remember, c sub 4 stands for the coefficient of the fourth degree term. So that means that I need the coefficients for the x to the 0 term, the x to the first, x to the second, x to the third, and x to the fourth. So I'm basically trying to organize it in table format to kind of keep up with these things. So we start here with our function. So our function is cosine 2x. And then we evaluate it at x equals a. So f of 0 in this case, because x is 0, would be cosine of 2 times 0. So that's cosine of 0, which is 1. So that gives me c sub n. So this would be c sub 0 is 1. So this is my 0 column. So then I'm going to go to my first coefficient. And so I need to use f prime of x, which means I need to take the derivative of cosine 2x. So doing chain rule with that, I end up with negative 2 sine 2x for f prime of x. Then we evaluate that at 0. So we have negative 2 sine of 2 times 0. So that becomes sine of 0, which is 0. So c sub 1 is going to be 0. Then we're going to do it for n equals 2. So we need to find the second derivative of this function. So now we do the derivative of negative 2 sine 2x. So doing chain rule with that, we end up with negative 4 cosine 2x, which we then evaluate at 0. So we end up with cosine of 0 again, which is 1 times negative 4. So c sub 2 is negative 4. So then we move to n is 3. This can become a very tedious process. Obviously, if they asked you for like the 12th degree Taylor polynomial, this would become exhausting. But it's not too bad. So then we do chain rule again, and we end up with positive 8 sine 2x, which we then evaluate at 0. And we get 0. And then one more time, so we need to go all the way to the fourth degree. So the fourth derivative, we usually write it in little parentheses like that once we go past 3. And so then the derivative of 8 sine 2x is 16 cosine 2x, which we then evaluate at 0. And so we get 16 for it. Okay, so now that last column there becomes the coefficients in front of my x minus a to the n terms. So since a is 0, my first coefficient is a 1, and it would be times x to the 0. Then my next coefficient is a 0 times x to the first. My next one is a negative 4, which would be times x squared. But remember, we do it, it's c sub n we do it over n factorial. So this would be over 1 factorial, this would be over 2 factorial, 3 factorial, 4 factorial. So remember, 0 factorial and 1 factorial are just 1. Here we would have over 2 factorial. Then we would have plus 0 x to the third over 3 factorial. And then plus 16 over 4 factorial x to the fourth. You could leave it written like that, but let's be honest, there's some things that we can very easily clean up in there also. Like x to the 0 is just 1, so my first term is just a 1. 0 times anything is 0, so that second term actually goes away. Now with these factorials, they actually usually don't simplify them. So even though 4 over 2 factorial is easy to simplify, most of the time you're going to see it continue to be written in factorial form like that. So there's no reason for you to not write it that way. Then our next term, we've got that 0 there, so the x cubed term would go away. And then the last one, we would just write 16 over 4 factorial, even though that could simplify, times x to the 4th. So that function models the behavior of cosine 2x. So this is our Taylor series, and so we usually call it a capital T, and we put the number down there for which degree that we went to. So this would be the 4th degree Taylor polynomial, so we call it T sub 4. This function models the behavior of cosine 2x, like I said. Now I also told you that I was going to do this a second way. So they told me that this was centered at 0, which means that this is a Maclaurin series. And if you go look at, I'm going to add another page in here. If you go look at your table that we have of the Maclaurin series, notice that we have one for cosine of x. So this is what it would look like for cosine of x. Cosine of 2x then is going to be very similar. So let me write down what cosine of x was up to its 4th degree term. So to its 4th degree, we'd have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So if we want cosine of 2x, all we do is we go replace our x's with 2 x's. So the 1 would stay a 1, and then this would be 2x squared over 2 factorial and 2x to the 4th over 4 factorial. Now, does that look like what we just did the long way? Well, we do a little bit more math. 2 squared is 4. 2 to the 4th is 16. And we do end up with the same answer. The only way you could use this approach, though, is if, number one, if they had given you the Maclaurin series for cosine of x, written it out for you, or if you had taken the time to memorize what the Maclaurin series for cosine of x was. Otherwise, you have to do it the long way like I did here. But either way, your answer is this for the 4th degree Taylor polynomial. All right, so one more example that we're going to wrap up. Now we want to find the Taylor series for f of x equals e to the x at x equals 0. Now, first off, this is a Maclaurin series, and e to the x is exactly written in there. So yes, I could just write it down straight from my chart. But I want you to pause the video for a minute and see if you can do the long way of coming up with this Taylor series here. All right, so this problem was a little bit different from example 1 because in example 1, they actually told us what degree to go to. They wanted the 4th degree polynomial. Here they just said come up with the Taylor series. So what that means is that our answer is actually going to be written in sigma notation. So that means we need the formula for the nth term in this e to the x Taylor series here. So that being the case, I kind of started to write out a few of my derivatives, and you may have realized this right off the bat. But notice it doesn't matter what derivative I'm looking at, the derivative is always e to the x. And if I'm going to evaluate it at my center, I'm always going to get 1, which means that my coefficient then is going to be my nth derivative evaluated at 0 over n factorial. Well, the nth derivative evaluated at 0 we just established is a 1. So 1 over n factorial is always going to be my coefficient. Like all of my coefficients are 1 over n factorial. And so my terms, if I was actually going to try to write some terms out, my first term would be 1 over n factorial times x to the 0. So it would just be a 1 because it would be 1 over 0 factorial. And then plus 1 over 1 factorial times x. and then plus 1 over 2 factorial times x squared, and then 1 over 3 factorial times x cubed, and so on and so forth. And so if you think about it, your nth term is going to be 1 over n factorial times x to the n. That nth term then helps me to come up with the sigma notation, because that's exactly what we stick into our power series notation. So we would say that e to the x is equal to the sum from n equals 0 to infinity of, and then we insert the nth term there, 1 over n factorial times x to the n. So that is my final answer for the Taylor series. So if they don't tell you a particular order to go to, that means they want the sigma notation instead of some terms for it. So we're going to wrap up here with just some important things for you to remember about Taylor and Maclaurin series. So the first thing is that the Taylor polynomial for a polynomial, so if they give you a polynomial function and tell you to come up with a Taylor polynomial for it, well, since it's already a polynomial function, it is the Taylor polynomial. The Taylor series then of a derivative or of an antiderivative is just the derivative or the antiderivative of the terms in the Taylor series. So kind of like what we did with power series. If the functions are related by derivatives or integrals, then their series are going to be related by derivatives or integrals. The Taylor polynomial of a sum or product is just the sum or product of the Taylor polynomial. So for example, if my function was e to the x plus cosine x, then I could just take the Taylor series polynomial for e to the x and the polynomial for cosine of x and put them together to come up with the Taylor polynomial for e to the x plus cosine x. So we can deal with the terms individually and then just combine them. Also, the Taylor series of a composition would just be the composition of the Taylor series. So that's kind of like how I did the cosine of 2x. I took the cosine of x series and then inserted the 2x into it because 2x was inside of the cosine function. And then lastly, when there is a composition with other operations, you want to do the composition first. So for example, if I had f of x equals e to the x squared plus cosine 2x, I would want to come up with the series for e to the x squared using that composition of x squared in place of the x, and then come up with the series for cosine of 2x using the 2x into the cosine of x series, and then I would worry about adding them together. So you always do the composition or the kind of like the u substitution portion prior to any addition or subtraction or anything else that we do with the Taylor series. So at the end of your notes, you have a couple practice problems that I would like for you to try on your own, and we will discuss them when I next see you.